Okay, picking up where we left off, continuing to work these problems that are definite integrals, trying to find the area bounded by these graphs. We didn't quite get to this example on the previous video. That's okay, we'll just pick it up and we'll do the next page also. And here we see we have an absolute value function, which, if you remember your pre-cal skills, look kind of like a V. Your typical absolute value function is a V. It's kind of got that vertex at the origin. The slope of the right side is a positive one. The slope on the left side would be a negative one. And here we can see we do have a little bit of a transformation. It's going to be shifted a little bit, shifted 1/2 to the right. And then it's also going to have a little bit, actually, no, I don't think it really does any shift. Or it may have a slope twice as big, I guess, because of the 2. Okay, so if we were to take this new graph, how you make sure you get it right, just plug it in, right? If I plugged in 1/2, 2 times 1/2 would be 1, 1 minus 1 would be 0. So 1/2 is where it actually is going to have the vertex. And then you could always just plug in x values and plot the points. If I plug in 0, you get -1 inside. The absolute value of -1 is 1. Same thing if you were to plug in 1, or if you were to plug in 3, which is the right side of this interval. 2 times 3 would be 6. 6 minus 1 is 5. So on the right side, x equals 3 is going to give me y equals 5. And that diagram may not be to scale, but it's okay. Okay, now this graph happens to be geometric, so we could use geometry. We're going to do that in a little bit to check. But what's nice about linear functions or absolute value functions is that it's either going to be a trapezoid or it'll be a triangle. And so here we got the triangle on the left and we have this triangle on the right. So I could use geometry to find the shape of that triangle, and then I could use geometry to find the shape of that triangle, and I could just add those two areas together. And that would be the value for this definite integral. We'll do that to check, but how do we actually do this absolute value with calculus? Well, we really don't want to fuss with integrating the absolute value. It's much easier if we could just graph the regular linear function. So instead of the absolute value of 2x minus 1, if I could just work with the function 2x minus 1, that would be much simpler. We don't want to integrate while we have the absolute value signs. So what we're going to do is we're going to drop them. Now, what you need to remember is when you drop the absolute value, sometimes something is going to happen. So let's look at the definition of your absolute value. If you were to take something like 5, I know the absolute value of 5 is 5. So if your input is 5, what you get out is the exact same thing, right? If I plug in 5, I get out 5. I get out the same thing. Or if I had a 17, I know the absolute value of it would be 17. So if x is 17, that means the y value is 17. I get out the exact same thing that I plug in. Okay, now if I had any positive number, a, if I plug it in, the absolute value of a is going to be a. So if my x value is a, then my y value is a. You get out the exact same thing that you plugged in. Okay, so that's really nice. When you're working with a positive term, it doesn't really matter if you have the absolute value bars or if you don't. There's the same things, right? The absolute value of 5 is the same thing as 5. The absolute of 17 is the same thing as absolute 17. The absolute value of any positive number a, including 0, would be the same thing as just that regular number by itself. So when I'm working with positive terms, I can just drop the absolute value and nothing happens because the absolute value of something positive is that exact same something positive. So that's what this top line means. When I'm working with a positive term, when I see this absolute value bars, I can just drop them off. And instead of having the absolute value, I can just have that regular old a because it's the same thing. Now, what happens if we have a negative input? If I plug in something like -3, the absolute value of -3 is 3. So here, if I plug in a negative, I don't get out the exact same thing. I get out the opposite version, right? I get out the positive version of that number. If I were to plug in, how about like -6? The absolute value of -6 would be 6. So I don't get out the exact same thing. So the absolute value of a negative term is not the same thing as that term by itself. But what you get is the negative version of your input, right? 3 is the same thing as -3. 6 is the same thing as -6. So whatever my input value is, if I take the negative version of that input, the two negatives cancel, and that's what your absolute value function would output you as. So all that is just to say, whenever we're working with absolute values, we don't really want to keep the bars. We want to drop the bars. We don't want to work and have these absolute value bars in my equation. So I'm going to drop them. Now, if I'm working with a positive term, I can just straight up drop the absolute value bars and nothing happens, because the absolute value of something positive is that exact same something positive. But when I'm working with a negative term, the absolute value isn't the same thing as that term by itself. The absolute value we know is the positive version. So how you make a negative into a positive? Well, you just multiply it by a -1. So here's kind of the summary. When you're working with absolute values, if you have a positive term, if the stuff inside the absolute values is positive, you can just drop the absolute value bars and you're good to go. But if I'm working with a negative term, if the stuff on the inside was negative, when I drop the absolute value bars, I need to pick up a negative, because that negative is going to turn my original value into a positive result. Okay, so a little bit tricky. Just remember, if your term's positive, drop the absolute value bars, nothing happens. If your term is negative, when I drop the absolute value bars, I need to make it positive, and putting this in there accomplishes that. All right, so I don't want to live and I don't want to integrate with this absolute value function. We want to work instead with, I know that was a dramatic reveal, we want to live and we want to work with the regular linear function, or whatever was inside the absolute values. We want to work with this function without the bars. Okay, so how do we do that? Well, let's think about the differences. This triangle right here, it would count as positive since it's above the x-axis. And this triangle right here would count as positive. So I know to integrate, to find the area bounded by this absolute value function and the x-axis, both of those regions should count as positive, right? And all your area is positive for absolute values. That one's probably also not going to be to scale. Now, if I were to integrate from, 0 to 3 of just the 2x minus 1, right? If I were to find that net area bounded by this linear function in the x-axis, this region would be fine, right? This area, the area bounded by the absolute value, and this area, triangular, bounded by the regular linear function, they would give you the same thing because they're the exact same shape and they're both above, so that one's positive and that one's positive. Now the issue is that this is going to get you your net area between 0 and 3, but now this area, this little triangle, since it's below the x-axis, it would count as negative. But my question shouldn't have anything counting as negative. So here's kind of the big trick for absolute value bars. You're not going to work with them. You don't want to integrate while you have this here. You're going to drop them and you're going to work with a much easier function. But you need to remember, when you drop the absolute value bars, anything that becomes negative, you need to make positive to make sure that I don't end up counting this area as negative. I want to make sure I'm getting this area, which is the same size, it's the same shape, it's just above the x-axis. So when I drop the absolute value bars, what I'm going to have to do is split this integral up, and then any region that was beneath the x-axis, I'm going to need to multiply it by a -1 to make sure I don't get the negative area. I need to make sure I get the positive area. Okay, so that's what we're going to do. Take this, and we're going to drop the absolute values, but when I do that, I'm going to have to split it up. So this integration, finding the area bounded by the absolute value function between 0 and 3, that would be the same thing as integrating the linear function 2x minus 1 plus the same integration 2x minus 1. But if I take the area from 0 to 1/2, and then I take the area from 1/2 to 3, I don't have to do anything here. Because integrating, right, if you think about from 1/2 to 3, integrating the absolute value gets you this region. Integrating the non-absolute value gets you this. But those are the exact same triangles, and they're both above. So I don't have to do anything here. The stuff that was positive, you can just drop the absolute value bars, and nothing happens. But this term, right, if I were to calculate it, this integral would give you this area. Since that area is beneath the x-axis, this would be a negative result. I want to make sure that this doesn't count as negative. So how I'm going to make it positive is I'm just going to stick this negative out in front. That negative, think about it like a vertical reflection. It's going to take this area, this little region that was beneath the x-axis, and it's going to flip it, and it's going to make it positive. Okay, so that is how you deal with the absolute values. You drop them, but then when you drop them, any region that's beneath the x-axis, you have to make it positive. And now we could go through and we could finish this integration. So I would integrate x squared minus x, and then I'm going to have to evaluate by plugging in the 1/2 and plugging in the 0. Let's do the other one too. It's going to integrate the same, x squared minus x, but then this one would integrate from 1/2 to 3. Ooh, let's see if I can kind of get enough room. I think I'll probably be okay. So negative, I have the upper evaluation minus the lower evaluation. Plug in the 1/2. 1/2 squared would be 1/4. And then 0 squared minus 0. Okay, that's all 0. How lovely. That's going to cancel. And then plus, now I can do the evaluation for this second integral, which means I need to plug in the upper number, then subtract the plugging in of the lower number. If you plug in 3, 3 squared would be 9. So 9 minus 3. And then if you plug in the 1/2, you're going to have the 1/4 minus 1/2. Okay, so I dropped the absolute value bars, but since this region would be beneath the x-axis, I need to make it positive. So sticking in this extra negative, that's negative. Putting in the extra negative is now going to make this whole term count as positive. That's how we go through and do it. It's a little bit weird, but keep track of that negative. I integrate, and then I evaluate. So plug in the upper, then you subtract the plugging in of the lower. And then let's just go ahead and let's distribute all these negatives. So minus 1/4. Or here, let's kind of take one extra step. Here, I'm going to just leave this outside. Let's see, 1/4 minus 1/2, that would be a negative 1/4. Then minus 0. So I did this. That was a negative 1/4 on the inside. Then plus, let's simplify. 9 minus 3 would be 6. Minus 1/4 minus 1/2. This would be a negative 1/4 minus negative 1/4. Okay. And then let's take this negative. Look, that negative is going to cancel. So got 1/4 and a 1/4. That's 2/4. That's 1/2. So we've got 6 plus 1/2. That's a perfectly good answer. Or if you wanted to write it as 13/2, that would also be perfectly fine. Or if you like the decimal, 6.5. Right, so that's mathematically how you could, if you didn't have a calculator, how you could deal with the absolute values. You just drop them. But when you drop them, you have to worry. If your region, when you drop it, if that region's positive, you don't have to do anything. You just drop the absolute value bars. You just continue on your merry way. But when I drop the absolute value bars, if there's any regions that are beneath the x-axis, you need to make sure that you don't count the negative area. You need to make sure that you get the positive area. So putting in this extra negative takes that region and makes it positive. Okay, and we could check it, of course, by doing a Math 9 in the calculator. Get out of here, calculator. So Math 9, we were integrating from 0 to 3. You can do absolute values. You hit Math, and then you have to scroll to the right. So number, and it's the very first thing, abs. That's how you can get your absolute value bar. Sometimes the calculator takes a little bit of time to do these. Let's see how long this one takes. Oh, no, it wasn't too bad. And it did end up giving us the 6.5. That's rounding error on the calculator's part, right? But it does give me the 6.5, which is the same thing as your 13/2. So we know we did it right. We can check it with a Math 9. You could also check it with geometry, right? If I know these regions happen to be perfectly geometric, instead of doing the calculus, it would be perfectly fine to do geometry. I could do 1/2 base times height, and then 1/2 base times height. I could find those two areas geometrically and then just add them together. Let's do it really quickly. Let's do the first triangle. Let's see if I find some room. I'll do it down here. So here's me doing it geometrically. So the first triangle, I have 1/2 base times height. The base is 1/2. And the height is 1. And then that second triangle, you have 1/2 base times height. I know the height was 5, because if you plug in 3 to the function, you get out 5. Then I need the width. So that's going to be 2.5, right? It's 1/2 and then 2. So there's 2 whole numbers and then a half. So 2.5, aka 5/2. So I could use geometry, 1/2 base times height. That's the first triangle, positive since it's above. And then I could do 1/2 base times height. That's gonna give me the second triangle. So that's 1/4 plus 25/4. That's the same thing as 26/4. And look at that, 26/4 is going to reduce to the same 13/2, or the same 6.5. So when I see the absolute value bars, don't freak out. You're not going to work with the absolute value bars. If it happens to be linear, you can drop them, and you can just do everything with geometry. You can find the areas of the trapezoids, you can find the areas of the triangles, and then you can work with that. That's fine. However, we're going to see on the next example, we're going to see something that's not geometric. So how do we deal with those things that are not geometric? Well, when you drop the absolute value bars, if there's any regions that are negative, you just make them positive. And how you do that is by sticking in this extra negative at the end. Alrighty, cool. Let's move on to the next one. Which here we've got the absolute value of x squared minus 4, and we're going to find the area of that weirdly shaped graph. No, you shouldn't know what this graph looks like yet, but you should be able to figure it out. And then we're going to get the area bounded by that weirdly shaped graph between -1 and 3. Right? Accumulate all the area of this function. There's your widths of all your little infinitely small rectangles. We're going to compile them together and get that area of the region. Well, here's the function we are trying to get the area bounded by. I don't know how to graph that, so we're going to work with the much easier function, the non-absolute value. That's just a parabola. Oh, I'm off the screen, sorry. There's your absolute value. Drop the absolute value. We have just the parabola. Now I can graph this. That's easy. It's a parabola shifted down 4 units, right? Easy. 1, 2, 3, 4. It's going to have an intercept at 2 and at -2. So I know this is what your non-absolute value function will look like. I got that one graphed. But if I were to integrate x squared minus 4, if I were to integrate that non-absolute value from -1 to 3. Well, let's see, -1 and then to 3. You would get this region and this region, and that would be a problem. That region's okay because it's above, and if you were to look at the absolute value graph, it would also be above. But I know this region is going to be negative, and I don't want to accumulate anything as negative because I know this function would never be negative. But if you wanted to get the graph of the absolute value function, all you'd have to do is take this same parabola, and the stuff that is positive, you would just leave it exactly the same, right? So if you're graphing the absolute value of something, you just graph what the non-absolute value is, you graph what that regular thing is, and the stuff that's above, you leave the same. But the stuff that is below, I need to make sure that it is not below. And so all you'd have to do is take this little region that was below and then vertically reflect it. And then this weird little W, right, that region's the same. Then that region, it was the parabola, it gets reflected up to make it positive. And then that region was the same. That's what this absolute value function would look like. It's a parabola, but instead of it continuing beneath the x-axis, anything that's under just gets reflected, and now it's above. And what I want for the answer of this question is I want the area of this region, which is positive because the absolute value is above, and then the area of this region, which is positive. Now, we're not going to work with this. We're going to work with the easier one. But when I do that, I can't just do the total. I'm going to have to split it up. Right? So this intersection point is at 2. So I can go from -1 to 2. And plus, let's see if I'm still on the screen. Yep. Then the rest of it would be 2 to 3. So I'm going to split it up. Right now, this integral would tell me this area. Right? If you're integrating the parabola, you're going to get the area bounded by the parabola and the x-axis. Now this region and this region are the same shape, they're the same size, but this one's beneath the x-axis. So if I were to calculate this, you could math 9 it and check. This is going to be negative because this is going to tell you the size of this region, or the area of that region. Since it's beneath, it's going to be negative. I don't want that to be negative, right? Because I really don't want this region. I want this one. How can I make this negative stuff positive? That's how. You just stick that negative out in the front. When I drop the absolute value bars, I just split it up. Any region that was positive is fine, because if you're thinking about the parabola, and when you're thinking about the absolute value, both of those regions have the exact same area, right? Because the parabola was above and the absolute value was above. So it makes no difference if you have the absolute values or if you don't. The stuff that's positive, you just drop the absolute value bars, you don't have to do anything. But for the regions that become negative, you need to make sure they go back to positive. So you're going to drop your absolute values, but when you do, make sure you snag anything that would be negative, make it positive. Just stick that extra negative out in front. It's a little tricky, but it's not super difficult. Okay, now we got to integrate. So I've got 1/3 x cubed minus 4x. That part's going to evaluate from -1 to 2. And then I have it. The integration's the same, right? Because it's the same function. It's just going to be evaluated differently. 1/3 x cubed minus 4x. And that one is 2 to 3. Sometimes I like to set it up first before I start getting overwhelmed with all the math. Just set it up. Don't forget about this negative. I have the upper evaluation. So the stuff in here is going to come from plugging in 2. And then minus the lower evaluation. So I had the negative out in front. Then all of this stuff is going to be from your evaluation, plugging in the upper, and then plugging in the lower. And then we could do the next one. So this is going to come from plugging in 3, and then minus the lower evaluation, that's going to come from plugging in 4. A lot of the times I'll just kind of get this set up, and then I'll go through and start plugging in, okay, what actually goes into each blank. But sometimes that can be a little bit overwhelming at first. If you need to do one side at a time, that's fine. I typically like to just go all at once, but that's just my own preference. Okay, let's plug in 2. 2 cubed is 8. 8 over 3 is just 8/3. Minus 4 times 2, so that'd be minus 8. Then let's plug in the -1. -1 to the third power would be -1. So it's going to be a negative 1/3. -4 times -1 would be plus 4. And plugging in 3. 3 to the third power is 27. 27 divided by 3 would be 9. 4 times 3 is 12. Then if you plug in the 2, you're going to get the 8/3 minus 8 again. Now be careful. This chunk and this chunk doesn't cancel. So look, that term, that negative, you distribute. So this chunk is all negative, and then this chunk is all negative. So those don't cancel. Those are actually combined, and they're going to double. So be careful. Don't assume that those are going to cancel. Sometimes they might, which is nice, but they won't always. Okay, let's just go through and let's kind of do one thing at a time. I'm just going to drop these parentheses, distribute negatives. So 8/3 minus 8, distribute the negative, plus 1/3 minus 4. Oh, I can't help it. Right, that's -3. I'm going to combine a little bit. Distribute the negative, distribute the negative. Okay, we still have this one out in the front. If you want, you can combine some stuff, right? Just kind of do little bits at a time. But you can kind of choose how you get to this answer. I'm going to combine them. 8/3 and 1/3. This would be 9/3. 9/3 is the same thing as 3. So I have 3 and then a -12. So 3 minus 12. I think that's going to be -9. And then plus, let's see what we got here, -3 and a 8. So all that's going to be 5 minus 8/3 minus negative, that's going to cancel. So we have a 9 plus 5. So that looks like 14 minus 8/3. Like that's one acceptable answer. If you combine your fractions slightly different, like if you were to just distribute this negative, then combine all the over 3s, combine the whole numbers, you may not get the exact same thing. You could get something that ends up looking like 17 minus 17/3. That's the same thing. Both of those are equivalent. It's kind of hard to see. If you were to get them to the final answer, let's see. Let's do 14. Let's turn it. So that would be 14. How many thirds is 14? So 14 times 3. So that'd be 42. And then minus 8. So this is the same thing as 34 thirds. Let's check. 17 times 3. So this is the same thing as 51 over 3, so 51 thirds. Then I need to do 51 minus 17. It's going to also give you the same thing. So both of these, if you were to actually combine them to the final singular answer, both of those will be the same 34 thirds, right? It'd be 11.33333333, right? It'd be 11.3 repeating. I like the fraction a lot more than the decimal. Unless the decimal is like a 0.25, a 0.5, or a 0.75, I generally don't like decimals. Fractions are much nicer. Okay, so the whole idea with these absolute value bars is that you're going to drop them. But when you drop them, remember, you're working with a different function. Function's sometimes the same if your area is above, right? When you drop the absolute value bars, anytime that function's above, you just continue on your merry way, that's fine. But when you drop the absolute value bars, sometimes that function may be beneath the x-axis. You would need to make sure that you don't get the negative region. You'd want to make sure you take this negative region and make it positive, because you want this one, not the one that's below, and putting in that extra negative at the beginning is how it's going to work. Let's always check it, right? Math 9 is a really nice tool. Math 9, sometimes these ones will take a little bit of time, especially with the absolute values. So let's do x squared minus 4 dx. Oh, that one worked pretty fast, right? I got the 11.333. Let's see if it'll turn it into a fraction. 34 thirds, right? Which is the same thing as this. Lots of different equivalent answers, lots of different correct things you could put on your page. But there you go. Okay, 2 more. Okay, this one is going to have a nice little twist. The part A should be easy, and then the follow-up, I guess it's not A. I guess I'll make it A right now. Part A and then the part B. This part's going to be pretty simple. It says find the area bounded by this graph, the x-axis, and the vertical lines x equals 2 and x equals 0. I said those backwards. Oh well. Let's graph it. Okay, so let's see. I don't have anything in there. That's good. 2x squared. Oops, wrong one. Squared minus 3x plus 2. Okay, got my default window. Probably going to need to zoom in. So that's what the parabola looks like. I only really care about it between 0 and 2. I'm going to kind of make it a little bit wider. I'm going to go, how about -1 to 3? So, so that I get a little bit, oh my gosh. So that I get a little bit on each side. So -1 to 3. -1 to 3. And then the y minimum, we didn't need it to be negative. Let's see if this works. So there we have a pretty good graph of this parabola. 1, 2, it continues. It looks like the minimum happened slightly before. So this graph looks more or less something like this. And what we're trying to find is the area bounded by that graph between 0 and 2, right? Find the area bounded by this graph, the x-axis, and then the vertical lines x equals 0, and then x equals 2. So we're trying to find the area of this weirdly shaped region. That's okay. A definite integral is going to do that for me, right? The area of that region, if I integrate this function, 2x squared minus 3x plus 2, and if I integrate it from 0 to 2, that definite integral is going to give me the area of that weirdly shaped region, which is what the question wants. Okay, so let's finish this one. 2/3 x cubed minus 3/2 x squared plus 2x. So integrate, and then we have to evaluate. What's nice is plugging in 0 doesn't always cancel, but it will here. If I plug in 2, let's see, we're going to have 2/3. 2 to the 3rd power is 8. Minus 3/2. 2 to the 2nd power is 4. Plus 2 times 2 is 4. And then if you were to plug in 0, all those terms, since they have an x, they're all going to go away, right? So that's really nice. Just because you see this, don't assume that the lower valuation is always going to cancel. It does quite a bit, but not always, right? So just be careful. Then let's finish it. That's 16/3 minus let's see, that's 2, 6 times, 3 times 2 would be 6. Or if you need 2, 12 divided by 2, so that's 6 plus 4. So it looks like we've got 16/3 minus 2. That's a perfectly good answer. That's the same thing as 6 over 3, so 16/3 minus 6/3, 16 minus 6, 10/3. Okay, so the area of this weirdly shaped region is 10/3, which, by the way, on your calculator, you can do it. I believe it's, let's try. If I hit second trace, so if I calculate it, I believe 7 is going to give you the integration. And then lower limit for us was 0. Upper limit was 2, and it should fill it in, right? It actually tells you what that area of the weirdly shaped graph is. I don't usually do the integrations on the calculator, but sometimes I think it's kind of neat that you can see it. I'll typically do it from the home screen. So math 9, 0 to 2, and I already have the function typed in, so I'm going to do vars y1. And then I typically do all my computations on the home screen. But if you wanted to do it on the graph, you could visually see what's happening. So that's cool, cool little tip. Okay, so the part B is what's going to make this a little bit more challenging. Here we go. A vertical line x equals k. And k is just some constant, right? I don't know what it is. That's what we're trying to solve for. K is some number. But we have a vertical line, x equals k, and it's going to split the region from the previous example. It's going to split it into 2 equal parts. It says solve for k. Now, do not assume, right, the interval is from 0 to 2. Don't assume that you can just say, hey, k equals 1, because this graph may not be symmetrical. The area to the left of 1 and the area to the right of 1 may not be the same. If there happens to be symmetry, then yes, of course, the line that splits it in half would be exactly in the middle. But we don't know that this graph is symmetric. In fact, looking at the graph, it doesn't really look symmetric. So we're trying to figure out, where is this k value going to be, right? Here's x equals k. And we want to know, it may be to the left of 1, it may be slightly to the right of 1. I don't really know for sure. But we're going to figure out where is that vertical line going to be placed so that the area to the left and the area to the right, they match, right? Split it in 2 equal parts means that the left area is going to equal the right area. Okay, so let's think about this. The area on this left, if you were to integrate from 0 to k, so if I were to accumulate all the area from x equals 0 to x equals k, that's your left. And then if I were to integrate from k to 2, that's your right. Like if I integrate from k to 2, that would give you your area on the right. And then I know 0 to 2, that's the total. So if I wanted the total, I could take 0 to k plus k to 2, and I could set that equal to the total. And then like you could solve that. That would be a little bit more complicated, but you could solve that. Typically what I would advise though is instead of working with 2 integration, just figure out how to work with 1. So you could do left plus right equals the total, and then you could work with both of the integrals, plug in k's, plug in zeros, plug in 2's, plug in k's. You could do that, but it's not the easiest way to get the answer. Just think about it like this. I know left plus right is going to equal the total, and I know left equals the right. So if the total is 10/3, then I know each side is going to have to be 5/3, right? 2 equal parts, that means each part is 1/2 of the total. So I could just set up this equation, 0 to k, that's going to equal 5/3, because it's 1/2 of the total. And you could do k to 2, and that integration would equal 5/3. There's lots of different things you could do to get this answer. You could do left plus right, set it equal to the total. Or you could just take, hey, the left, it's going to be half of the total, 5/3. Or you could take the right, set it equal to 5/3 because it's half the total. If you know how big each area is, then you could just set up the one integral for that one region and set it equal to that one area. Could you go through and do other things? Yes. But I'm gonna solve this one. Why that one? Because it's got one integral instead of 2. And why this one over this? Because I like plugging in 0 more than I like plugging in 2. Both of those would give you the same thing. I'm just going to pick the easiest one that's going to get me to the answer. Okay, so I'm going to do this. So I'm going to set it up, the integration from 0 to k of the function. So we have 2x squared minus 3x plus 2. that's going to be equal to 5/3. And now I'm going to solve it. So I'm going to integrate 2/3 x cubed minus 3/2 x squared plus 2x. And then I'm going to have to evaluate it, which means plug in k for x, and then plug in 0. When I plug in 0, the whole lower valuation is going to cancel. So I'm just not gonna. I have 2/3 k cubed minus 3/2 k squared plus 2k. That's going to need to be equals to 5/3. And then I could solve this. You could bring this over. Minus 5/3 equals 0. And then if I were to graph this, you could graph, and since it's equal to 0, you could graph it and find your x-intercept. If you were to leave it so that it was equal to 5/3, right, you could graph this in y1, and then you could graph this in y2, and then if you graph the two things, you would be finding the intersection point of those two things. But mathematically, they like it more to get it all on one side, get that one equation, graph it, and if you want that one equation to be equal to 0, you're going to graph it and you're going to find the x-intercept. So let us do it really quickly, and then we'll be done with this, and we got one more. So get that out of there. You're graphing this. 2/3 x to the third minus 3/2 x squared plus 2x. Oh my gosh, I didn't get out of that exponent, did I? That was plus 3/2 x squared. At least I caught it. Plus 2x minus 5/3. Okay, I'm going to graph this, and then I'm going to find the x-intercept. That's cool. There it is. Let's go use the calculator. So we're going to use my GDC, my graphing data calculator, and then let's do second, trace, and then let's do a 0. Left bound, yep, click somewhere on the left. Right bound, we're using Newton's method, hooray, we didn't know that, but now we do, hooray. Now click on the right, do your infinitely many tangent lines, and then there we go. We're going to find that k value looks like an x value, but remember, you have to graph it with x, but visually what we're doing is actually solving for k. Calculator just always uses the x button. And then we find that it's 1.386 or 387. You can round it or you can truncate. They would accept both answers. Okay, so those questions are a little bit tricky. The part A was easy. If it gives you this graph and it says find the area, that's easy, integrate. But what comes up a lot, my diagram was not to scale. That line should have been slightly to the right of 1. That's okay, right? But the idea was we were trying to figure out where is that line that's going to split the area perfectly in half. Don't assume that it's at the midpoint. If the graph is symmetrical, yes, it'll be at the midpoint. But here, that line actually ended up needing to be more like this. Okay, but those can be a little bit tough. The general idea, though, is integrate to find the total. And then if we have some vertical line that is splitting the region and dividing it into parts, it doesn't always have to be equal parts. Like here it was nice. So we knew left plus right was equal to total, or we knew the left was half, and we knew the right was half. But your line may not always split it exactly in half. Maybe you have it so that the vertical line is going to split it so that 1/3 of the area is on the left, and then 2/3 of the area is on the right. Well, if you know the total, take that total, divide it by 3, and then you could go from your left side to your k and set it equal to 1/3 of the total. Or you could go from your k to your right side, and then that would be equal to 2/3 times the total. Right? If you know the total, you can find any proportion or any percentage of the total. Or let's say we have a k value that splits it so that 3/4 of the area is on the left, and then 1/4 of the area is on the right. That's okay. If you have the left, or if you have the total, you could do the total times 3/4. That's the size of this area. And you could integrate from the left to k and set it equal to 3/4 of the total. Or you could go from k to the right side and set it equal to 1/4 of the total. It really doesn't matter how that vertical line splits it. If you know the total, And you know how it's going to split. If it splits it into equal parts, that's 50%, that's 50%. Or if it splits it into 1/3, 2/3, or maybe it's 2/3 on the left, 1/3 on the right, or maybe it's 1/4, 3/4, or maybe it's 6/7, 1/7. They're usually going to split it in half or into thirds or maybe quarters. But if you know what the total is, if you know how the line's going to split it, you should be able to figure out geometrically how much area is on each side, right? It's just a percentage, like 1/4, 0.25 times the total, or 2/3 times the total. And then you would just set the integral equal to that specific number. Could you do left plus right equals total? Yes. But then you'd have two integrals to do, and then it's going to be a little bit more work. It's always easier to just get the one integral equal to that one specific area, then integrate, plug it in, and then solve. Okay, those are a little bit tricky, but hopefully they make sense. Okay, last little thing, and I'm just going to throw my notes key up underneath there so I don't have to redraw it. You know, it's kind of out of room. There's a subtle difference between net area and total area. Okay, net area is what a regular old integration is going to give us. Remember, that function f of x, if we're integrating it, we're accumulating all the area bounded by this function and the x-axis. This function could sometimes be above or sometimes be below. So just a regular old integration is going to give me net area. And assuming we're integrating from left to right, areas above, like regions 1 and 3, regions above would count as positive, and then regions below would count as negative. Again, that's assuming left to right. If you wanted the total area, so if you said, Mr. Bell, I don't really want this to count as negative, right? I don't care that's below. I just want to know how much area do I have, how much area do I have, how much area do I have. If you want the total area, which is different than the net, what you could do is just take the absolute value, because we know the absolute value is just going to take this region and then boop, flip it, and then make it positive, right? The stuff that was positive, taking the absolute value isn't going to change it. You'd have the exact same region. The stuff that was positive, when you take the absolute value, doesn't do anything. It's the exact same thing. But if you have a region that's negative, taking the absolute value is just going to reflect it and make it positive. And then if I integrate the absolute value, everything is going to count as positive, right? So net area is a regular integration. Some of it could be positive, some of it could be negative, and then they cancel out against each other. If you want total area, you would need to take the absolute value and then integrate. Notice, you need to do the absolute value first, then you can integrate. If you do the integration and then you do the absolute value, what you're doing is finding the size of the net area. And the size of the net area, when you do the integration, the positives and the negatives cancel out, and then you'd be taking the absolute value of the result. No, you would need to cancel out the negatives first, right? So you'd have to do the absolute value and then integrate. If you do the integration, that's when the net thing, the positives and the negatives are canceling against each other. You need to do the absolute value first, then integrate to get the total area. But a regular integration is net area. The absolute value would be your total area. It wouldn't really care, right? If that area is beneath, doesn't matter. You still have the size of that area, and the absolute value is how we can find the size pretty quickly and pretty easily. Okay, let us, by the way, if we have this property, remember, if I switch the order of integration, a to b is the same thing as the negative integration from b to a. So when I'm integrating from left to right, the stuff above counts as positive, the stuff below counts as negative. If you're working backwards, so if you're integrating from right to left, everything is reversed, and it's just because of this process. And we're going to work more with that in the future. But if for some reason I was ever integrating from the right to the left, everything is just the opposite. It's because of that little property. We're going to see that come up a little bit in a future lesson. Most of the time we integrate from left to right. So above is positive, below is negative. Okay, I think we have a couple more examples. Let's just finish this stuff, and then I think we'll be good. Actually, no, we're done, right? Because the next page has u sub with definite integrals, so that'll be the next video. Yeah, we're done. We're done with the stuff for today.